Okay, and now he's sharing. Thank you so much.
Yeah, it just helps. You walk away from it, it's easier.
Okay, let me. Yeah, sounds good. Yeah.
So maybe let me just follow
Yeah.
up. So I guess the question is, how clear is it that these insulating states are in fact Hall states
Right.
versus like,
Excellent. So this is why this is important. How the insulating states, it's the density of the insulating state linked with the magnetic field. So when you see this straight line, there's a Schroeder formula. There's a Schroeder formula saying that if you have a quantum Hall states, right? The density, if your chemical potentials is inside the quantum Hall gap, then as you change magnetic field, the density in the ground state will change linear with magnetic field, and the slope is a Hall conductivity sigma x1. So that's why you see these different slopes, mu equal 1 and all the way to 9. So you have integers. Slopes are exactly integers, and here these slopes are corresponding to.
But this is what's done in this type. This is closest to like an inverse compressibility.
It is.
that you're measuring.
It is compressible. Yeah, it is compressible. Compressibility tells you whether it's insulating or non-insulating. But you need.
I mean, you're measuring its capacity. It's basically capacity deduced from capacity.
Yeah,
It's compressible.
but you need still this two-dimensional parameters space density ratio magnetic field to show it's a quantum Hall insulating states.
right. So you're saying that although we can't see it super well in the top plot, this relationship continues into effect.
That's right. I'm not showing this. I'm just only showing a cut of the different magnetic field, but yeah, there is a dependence. Yes.
But what's the color scale in the color picture? You know, how high is the yellow or how low is the blue or what?
That's a good question. Yeah, that's a good question. So so in other words, the question maybe is this, from the color bar, right? And we know what kind of color bar means it's actually truly insulating states. That's a fair question. I don't know the answer. But these are standard measurements in the field from the compressibility
I get
measurement.
what you're saying. Let's say the lower picture is arbitrary units. The upper picture therefore is arbitrary units also. Or
It's I don't know if the upper panel has unit or not. That I don't know. But the lower one is up unit. Yes. Yeah. Next, yes, Andrea.
So the previous picture that you showed us, when
Yeah.
I has been
Yeah.
what density it corresponds to?
What density it corresponds to? So yeah. So actually, if you, for example, in a very wide density range, the doped holes will only occupy this first spin split band, but in a wide range of density.
So insulating states then will be within this picture.
So what happens is following. Okay, you first dope the system, right? You dope the system, you get a two-dimensional whole gas, which is a metallic state.
Right.
And then when you apply magnetic field, you get a quantum Hall effect of this two-dimensional electron gas.
Right.
And the slide I just showed you is about the quantum Hall physics. Quantum Hall physics.
So there's no separate insulating states without.
Not in this monolayer.
Okay.
Yeah, not in monolayer. Yeah, absolutely. You're absolutely right. In monolayer, the only way you get it. So here you got all quantum Hall physics. Yeah, I'm just trying to compare it with gallium arsenide basically. Gallium arsenide, you start with a electron gas, you apply magnetic field. When the sample is very clean, you get a quantum Hall, fractional quantum Hall physics. Similar things happen here. Yeah. Okay, so this is the base of the setup, but I'm going to now talk about the case of two layers stacking them together. So these materials are van der Waals materials. You can stack them together and in various combinations. So the whole is much bigger than the sum of the parts. And as you all know, that this whole field of moire materials really got people excited after the discovery of Mott and Chern states, superconductivity in physical particles, MIT, and also you can see that the moire structure in real space, and even early on there is some spectroscopy evidence that there is some flat band. So I'm going to focus on these semiconductor moire systems, stacking two layers of semiconductor TMD semiconductors. And it can be two identical layers, for example, twisted WSE2 layer. And in that case, just like in PPG, the moire period is due to the twist angle. But in the case of the TMD, there's another possibility, which is, I think is even more interesting. You can take two layers of different TMDs. And in that case, they will have intrinsic lattice mismatch, which is usually very small. And then in this case, even without any twist, this intrinsic lattice mismatch will lead to a superlattice structure. Okay, so basically now there are two control norms. The moire period can be controlled by both the lattice mismatch and the twist angle. So in the case of the homobilayers, the moire period can be arbitrarily large if you go to very, very small twist angles. In the case of the heterobilayers, then there's an upper limit. So the moire period will reach the maximum at the twist angle 0 degrees, and there will be an upper bound. So, one of the reasons I got interested in this semiconductor, this TMD moire system, is that conceptually it's much simpler. If you want to think about the moire band formation, why moire bands are formed. In the case, for example, WS2, WS2. Right? So this is again, how do you think about this moire bands? Well, first pointed out by Adam McDonald's group in 2018. And in these materials, again, if I just look at the two monolayers, right? In both layers, the valence band top is at the K point and K prime point. And but the two layers, because they are made of different materials, they have an intrinsic band offset. And in this case, the two band offset is very large. It's on the order of 300 megaelectron volt. And therefore, all of those holes is in the WSE2 layer. Right? So in this case, you may ask me, what is the role of WS2 at all? The role of WS2 is to just create modulation of the structure. Then make the WSE2 layer spatially corrugated. It's corrugated, right? So because of this spatial corrugation effect, it makes the valence band edge to be spatial dependent. So there's a spatial variation of the band edge due to the formation of the moire lattice. Okay, and this can be modeled then by a periodic potential. Right. So the electrons are all in this case, in the WSE2 layer. Okay, but now in addition to kinetic energy, there's an additional slowly varying superlattice structure due to the corrugation effect. Yes.
So is there any fundamental difference between this and why, for example, like you just said, the second layer doesn't play a role other than introducing this new period?
In this case, yeah.
Is this just the original butterfly physics where you just put the graphene on boron nitride? That also gives me, band folding.
It's even simpler than that. So it's similar to a graphene on boron nitride, indeed. But in the case of a graphene on boron nitride, as you know very well, the boron nitride also makes the two sublattices of graphene different. So in addition to create a periodic potential, it may also create a sublattice dependent potential, right? So which is modeled by a direct mass term. So here we are starting with not direct electrons, but just a single parabolic bands. So the effect is purely captured by the periodic potential. So that's why it's, in a sense, it's the simplest. This case is simplest. And in our calculation, I'm not going to show that, but in our calculation, what you can do is you do the large scale DF calculation for the WS2, WS2, and you optimize the lattice structure. You see that the two layers are both corrugated, and then you can even manually remove the WS2 layer. And you look at you keep this corrugated lattice structure of WSE2, and then you calculate the electronic bands. You find that it actually very well with this continuum model. Of course, you can also do the electronic structure application with both layers, both corrugated, but there's no essential difference. So this explicitly verifies that in this case, the role of the other layer is just to make the active layer corrugated. Yeah. So spatial corrugation already is enough to create this kind of a moire potential. Yeah. Okay. Yeah. So. Okay. So so in this case, then one thing I want to mention is that the kind of length scales and energy scales involved in these moire bands. So there's a characteristic kinetic energy scale which is just set by the moire wavelengths, moire period AM. And the second energy scale, which is the depth of the moire potential V. Right. So depending on whether the kinetic energy or the potential energy dominates, you are either in the near free electron limit or in the confined limit. And this competition is controlled by the moire period. Okay. So as you go to larger moire period, then the potential energy always dominates. So you are now in the confined limit, you get flat bands. And the way to think about the flat band is actually very simple. It's just that in this limit, the moire potential, I'm showing you a line cut of the moire potential in real space, and each potential minimum, you can think of this like harmonic trap, and you have localized electron states in each potential minimum, and there will be weak coupling between these potential minimum, and therefore it leads to a flat band. Okay. So it's also equivalent to think in terms of the length scales. There's one length scale which is the moire period. There's another length scale is that if you treat each moire potential minimum as a harmonic potential, and there's electron in the harmonic potential, it has a confinement length, which I call C naught. And C naught is basically determined by the curvature of the harmonic gap, which is basically potential strength divided by the moire period AM squared. That's why it has this form. Again, you can see that C naught goes as the square root of AM. So in the large AM limit, C naught is small compared to the distance between adjacent potential minimum, and therefore the electrons are tightly localized to each potential well, and again you get flat band. Okay, so this all looks quite simple, but on the other hand, if you think about when we add interactions, right, what we have is this is a Hamiltonian in first quantized form. You have kinetic energy, you have a potential energy, and you have electron-electron interaction. So this Hamiltonian, if you think about it for a minute, it's exactly the same form as the universal Hamiltonian for all solids, for all crystals, right? So if you think about the natural solids, like silicon or sodium chloride or anything like, right? So there's ions which form a lattice periodic structure. And then ions provide a external potential for electrons. So it's a periodic potential. And then electrons with coulomb repulsion among themselves. So it has exactly the same form as this Hamiltonian. Right? So that's why I think of this semiconductor moire system as an artificial solids. Right? And it's highly tunable because you can change the moire period and vary the dielectric environment. So you can change the filling factor. Most importantly, you can change the filling factor. In a real solid, the number of electrons per atom is always an integer. Here, the number of electrons per unit cell is controlled by electrostatic gating. So this, I think, leads to already should lead to enough interesting things. Yeah.
Oh, no, that was exactly what I was going to ask. So here you can put many electrons.
You can put many electrons. You can put 1, 2, 3. You can even put 1/3, like 1/3 of electron per unit cell on average, right? So that's why, and people do see interesting states, so-called generalized when they put within crystals, like 1/3, 2/3 fraction phase, right? So one important difference is that in the real solids, the potential of the ions is highly singular in the core, right? So cool. But here, the potential we are dealing with is an effective long wavelength potential due to the lattice corrugation. So it's much more smooth and it's slowly varying. So from the original Allen's paper, because of any smooth periodic potential, you can express in terms of Fourier components. So it's very often people will just take the leading order, the 3 lowest order harmonics, which are related by symmetry. Because of the potential, because of this lattice has triangular symmetries, so take the 3 lowest Fourier components. This is a working continuum model for the semiconductor moire fit. Yes.
When you tune the density by gating, how much control do you have over the effective number of dopants, meaning like being at commensurate versus incommensurate?
So the density vector is continuous, right? Continuous.
Right. But like if I look at a material, it's like sometimes so like famously the story of like doping a Mott insulator, right?
Yeah.
So I have a Mott insulator, I have to be an exactly integer filling, and then,
Right.
you know, I put a few holes in and I get this, you know, effective.
Right.
Interaction that maybe looks quite different. So I guess the question is like, can you control the density to be like, yes, we're totally commensurate, or is it always kind of?
I mean, there's always some homogeneity, for example, right? But you will see, I'll show you the data that actually integrating something happens.
Yeah, okay.
So, you know, the last several years, you know, the experiments on this TMD really revealed a whole slew of interesting physics of matter, including Mott insulators, Wigner crystals. There's an electric field tunable continuous metal insulator transition. There's a quantum on-Hall states, also heavy liquids. A lot of the experiments on TMDs are done with optics. It turned out that apparently there's some light-induced mechanism still being understood. Also recently there's a report of exotonic physics of matter. And then even more states are being proposed, fractional transits, quantum spin liquids, superconductivity, spin tolerance, and pseudo metals. It's remarkably rich. Yeah. So I'm going to focus just on the state integer things. Let me start with this Mott insulators. So, again, if the molecule is large, if we're in the sort of a tight binding regime, this doped charges are basically tightly bound to this moire sites, which are the potential minimum, and therefore the effective Hamiltonian is a periodic array of these sites coupled by electron tunneling T, and there's a density interaction. So this Hamiltonian was first written down by Allen's group, and they advertised these TMD semiconductor heterostructures as a quantum simulator for Hubbard model. Later I'm going to examine the applicability of this Hubbard model description. But you know, this is what got everybody does started working in this field first by this approach. And in terms of the energy scales, so when the molecule AM is large, the bandwidth T is exponentially small, right? In AM over the quantum confinement length T0. So it's the smallest energy scale. The on-site interaction, you know, which is E squared over C0. C0 is the size of the electron weight packet confined to a single moire site. So this is the largest energy scale, and in between there's an off-site, for example, nearest neighbor interaction, which is E squared over AM. So there's this hierarchy of energy scales. So now, if you have a Haibani Hubbard model like this, and when interaction on-site interaction U is large enough, you expect the insulating state at the fitting of one particle per site, right? So this is basically a Mott insulator, and indeed, this was observed in 2020 by both the Cornell group and simultaneously the Berkeley group. So this is a carrier density in units of the fitting, the number of particles per unit cell or unit cell, and you see that there's some very highly resistive insulating states at the fitting of one charge per site. And this is the WS2, and it appears when the molecule AM is large, or 8 nanometers. The same system, but when you work at a molecule of 4 nanometers, when you introduce a finite X angle, then this insulating states disappear. Okay, so this is again telling you that in a large molecular limit, you do get Mott insulating states at the beginning of 1. Yes.
Is there any signature of magnitude?
Yes, I'm coming to it now. Yeah. Right. So one of the hallmarks of the Mott physics is that there should be a local magnetic moments, and this is again the great thing about the semiconductor TMD field. One can probe the local moment magnetism using optics. That's not possible in graphene. Okay. So so there's a huge amount of experimental studies of optical properties of monolayer TMD. This has been studied for as long as graphene, for almost 30 years. So because of the spin up and spin down are locked to the values, so you can and the optical selection rule is different at the value k and k prime. So one can use the circular polarized light to selectively probe the occupation, the value occupation. Okay, and here I'm showing you the experimental data using both left and right circular polarized light at the zero magnetic field. This is basically the reflectivity as a function of the photon energy, and you see the optical response is the same as zero magnetic field, but when you apply magnetic field, they become different. Okay, so you take the difference between the left and right circular polarized light, you get something called magnetic circular dichroism, and you plot that as a function of magnetic field. Okay, and you get a behavior that's shown here. The red line shows what happens without any charge in the system, So it's essentially flat, but when you put one particle per unit cell, moire unit cell, you see this behavior, which looks very much like magnetization curve. Right, so with a small magnetic field, the magnetization rises up very quickly, saturates, and then saturates. So this is again consistent with this magnetic dichroism is tracking the amount of value propagation. Okay, and if you look at the slope, right? If you look at the slope, you can think of this being similar to some kind of spin susceptibility, and we plot the spin susceptibility as a function of temperature. And you find that it has a periodic behavior with a 1/T with an offset. And that offset in this material, the residue is very small, but it's negative. It shows you that there is a weak anti-prime interaction that's present. Okay, this is really a very clever way of probing mechanism that's from the compound group. Okay, so far everything good. So now let me, so everything looks very, all just a simple triangular cover model. When I started thinking about this, what we noted is that if you look at the most general form of the moire potential, right? As I said, it's a sum of three lowest Fourier components. But when you sum three Fourier components, it allows a phase factor phi. And what this phase factor phi does is control the landscape of the periodic potential. So for example, when phi is 0, this moire potential is it looks exactly like the triangle lattice. It has a 6-fold rotation symmetry along the potential minimum. But when phi is, for example, 60 degrees, then you get a honeycomb potential. The moire potential minimum form a perfect honeycomb lattice. And if it's in between 0 and 60, it could be more triangle lattice-like, or it could be more honeycomb lattice-like. Meaning that in the first case, you only have one type of potential minimum. There's a single potential minimum within the unit cell. This is the case for phi equals 0 and phi close to 0. But when phi is equal to 60 or closer to 60, you see in addition to a primary minimum, there's also a secondary potential minimum. So now you have to deal with if you want to single term the pi binding description, there are two types of potential minimum, there's two types of sites. So it should be generally described by a honeycomb lattice model with some potential bias between the two. Okay. So and indeed, if we look at the band structure of these different materials, for MOSE2 and WS2, this band structure is exactly what we expect from just a triangle lattice. The first band comes from the S orbital at every side. The second and third band are nearly degenerate, come from the PX and PY orbitals on every side, right? On the other hand, for WS2, WS2, the one that I just showed you, if you look at the band structure, the first two bands are not at all like the triangle lattice. The first two bands actually can be fitted quite well with a honeycomb binding model with a potential bias between the A and B sides. Okay, for example, if you look at the band gap, it's not at the gamma point, but at the kappa point. Okay, this is exactly what you expect for honeycomb binding model with a sublattice potential difference.
So my recollection is for twisted bilayer graphene, the moire potential is only periodic up to phase. From going one lattice point to another, but this is really periodic.
Yeah, it's really periodic. Yeah, that's fine.
Yeah. The slides are not moving.
Oh, slides are not moving. Okay.
Yeah, stop sharing and then share.
And then share again. Yeah. I think I need to first share the. Let me try. Does it work now?
Let's see.
Does it work?
Yeah, keep going.
Okay, all right, yeah. Okay, so anyway, not to too much, but you know my postdoc Yang Zhang did a really heroic amount of large scale DFT calculations for various materials, and you know he summarized. And then for every manufacturer, you try to extract this continuum model parameter, the phase phi, and as a function of a period. And you know, but the punchline that for many different materials, they're could be really described by asymmetric Huntington lattice instead of the Chern lattice. And why this is important? Now, actually, thinking of one electron per unit cell, you know, in this modeling swing space. And in any case, electron will occupy the primary potential minimum. So it might seem like not much of a difference. However, things become different if you load electron above k factor 1. So if it's if the electron potential has only a single minimum, you load it above the k factor 1, you get an energy cost of Hubbard U. And in this case, you get so-called more Hubbard insulator. But if you have two types of moire sites, right? And the primary moire site has one electron everywhere. And if you now dope an additional electron, when the energy difference between the primary and secondary minimum is small, the dope electron will prefer to occupy secondary site. So in this way, it avoids the Hubbard on-site interaction U. So this means that the system is really a charge transferring system. Okay, so both electrons above k factor 1 occupy a secondary site to avoid the on-site gluon interaction U. And this is actually the case for example, high temperature supermassive filters. And so we believe that in many DMD semiconductor heterostructures, including WS2, WS2, at the k factor 1, the system is really a charge transfer insulator. The insulating gap is actually determined by the charge transfer energy delta rather than Hubbard U.
What's the range of delta value?
Right, so it's usually on the order of a few tens of millielectron volt to 100 millielectron volt. And later I'll see that in some systems, the tunable by applying electric field.
Can you also comment what you know, given the lattice constants in play, what would you expect the magnitude to be?
Well, the magnitude, oh yeah, exactly. Yeah, it's an excellent question. So if you use this this simple estimate that based on the quantum confinement length, the size of electron potential well, and you put in E squared over epsilon C naught, you get something typically around 70 or 80 millielectron volt. It's very large. It's big compared to the charge transfer energy delta. Yeah. So we have been advocating this charge transfer scenario for a while, and people just like the simple Hubbard model picture. But finally, Xiaodong Xu's group at University of Seattle, they studied this system at the dopings above k factor 1. This is y-axis is the date. So 1 is the monitoring state, and the doping all the way to k factor 2, right? And now, if we take the point of view of just a single Hubbard model on the Chern lattice at k factor 2, every side is double occupied. There should no longer be any local moment. But experimentally, you see that this magnetic circuit diaposal as a function of magnetic field, you see also strong signal at the k factor 2. Right, this MH curve, what looks like behaves like an MH curve. It's not featureless at k factor 2. But this can actually be understood naturally if you take a point of view of a two-band Hubbard model. Right, you have both two types of sublattices, moire sites, At filling factor 1, all the electrons occupy the primary site, small insulator. And if you go above filling factor 1, the additional electrons go into the secondary site. And when you go to the filling of 2 per unit cell, both the potential primary and secondary sites are fully occupied. And in this case, you get a unicomplexed small insulator, and you still get local magnetic moments. Right, so that's fully consistent with the picture of a charge transfer insulator. And there's also, I learned recently that there's some STM experiments that directly look at the electron wave function at filling factor 1 and at filling factor 2, and they do see this honeycomb behavior. Yeah, honeycomb behavior. Okay, so far it's about the modern insulating states. Now, a real surprise came from the Condensed group again in 2021. They found that in another heterostructure, MOT to WSE2, in this case, they are able to map out the transport result. This is really transport from resistivity measurements as a function of the top and bottom gauge. So this allows them to control both the carrier density and the electric field between the 2 layers independently. Okay, so these are the 2 axes. Don't ask me why it's blended, I have no idea. If you go along this axis, you are increasing the density. Along this axis, you are keeping the density fixed by the change in the electric field. Okay, so again, you see that filling factor 1, you see the higher insulating state, modern insulator. But as you increase the electric field, something else happens. And this turns out to be a function non-small state. I'll show you next. And so all this is obtained at constant filling factor, 1 electron per unit cell, 1 hole per unit cell, by just changing the electric field. There's a quantum phase condition induced by the electric field. So, this is also why the charge transfer picture becomes important. We will see that when they showed me the data, my first thought is that the electric field is actually changing the charge transfer between the 2 layers. Okay. So we first look at just the band structure, non-impacting single particle band structure for this problem. So what makes this system interesting and different from all others? I should mention that I asked the Cornell group how did they land upon this material, right? And they told me they tried all combinations, and in this one, they found something new. Okay. So okay, then we did the DFT calculation, and it was interesting that in this case, the band offset between the MOT2 and WS2, the work function, the difference is the smallest. Okay, among all the possible combinations, it's only about 130 millielectron volts at a 0 applied electric field. So when you further apply electric field, you can reduce this charge transfer energy, and you can even start to invert the bands between the 2 layers. And this is why the electric field can create a band inversion. That's the basic function. Okay. So again, here is the result from the DFT calculation by Liang Fu. We do exactly what I said earlier. You choose 13 by 13 unit cell superlattice with 13 by 13 unit cell in MOT2 layer, and then this is nearly commensurate with the 14 times 14 super cell in WSE2 layer. And within the calculation, we first optimize the structure. So in the optimized structure, both layers are corrugated.
Yeah.
The MOT2 layer is corrugated stronger. Yeah.
The range of energies in the Waals picture, is it different than the one in the other picture?
It's different. Yeah. And what is shown here is that you take this optimized structure and then you remove the 2 layers. Right. I will just illustrate first the physics. So you keep the corrugated structure, but you remove the 2 layers apart from each other. Then you can look at the moire bands in each layer separately. Right. That's what I'm calling here. Because of the corrugation, instead of a simple parabolic band, you see that it now folds into many bands. And in the DFT calculations, the value K and value K prime, they always see them together. So conceptually, they are really independent. They are separate by large momentum in K space. but in the actual DFT calculation, well, they're always two together. So I cover them differently. So we just need to focus on the red bands, which come from value K. The one from the opposite value is always the time reversal partner. So just focus on the red band, or say blue bands. No, okay, blue bands. All right. So if you look at the MOT2, the first moire band has a minimum at the kappa, corner of the middle. And then if you look at the WSE2, the top of the first band is also at kappa. Okay, and just as you asked, right now in the separate monolayer calculations, we don't know the band offset between the two, right? So that's why we need to put them together. So this is a calculation including both layers, again, DFT calculation. At the zero displaced electric field, the bottom of the MOT2 layer, the band bottom is above the band top of the WSE2 layer. Okay, and with an energy difference, which is about a few tenths of megatron volt. But as we increase electric field, we are pushing the energy of the WS2 layer up. So eventually the gap closes and then reopens. Okay, so the electric field basically inverts the top of the WSE2 layer and with the bottom of the MOT2 layer band. It creates that inversion. Yes.
The in-plane electric field.
Electric field, but that would create a conductivity, that's the current transport.
Would it affect the band structure?
But once you apply electric field, you get a current, not in the wrong state. Okay, so I'm not going to into all the details, but basically electric field inverts the bands, the mini bands. At the same time, there's also interlayer hybridization. It turns out interlayer hybridization is small, but it's still important. The interlayer hybridization creates a P-wave mixing, and combining the two, this band inversion is exactly captured by the Dirac fermion with mass changing sign. Dirac fermion with mass changing sign, so this leads to a topological phase transition. Okay, after this, the band gap is after the gap is inverted, we get a Chern number. The Chern number is +1 in value k. The time reversal symmetry guarantees that also Chern number of -1 in value k prime. So the whole system, is in the non-impacting picture is time reversal invariant. And this means that, for example, at K factor 2, you fully occupy the bands from both value k and value k prime, both swing up and swing down. This means that electric field can tune the system from a band insular into a quantum swing point. Okay, and indeed, this is what our theory of DFT calculation says. And there's some recent paper on the archive from Cornell group that shows that indeed there's some evidence of the edge-state transport. Quantized, it's on the order of e per h per edge, that's consistent with quantum small states. Okay. So what I'm showing you is basically going back to the space diagram. So within this sort of a band structure calculation, we can understand the case of K factor 2 from band insular to the time reversal numerical insular. But what's most interesting is what happens at halfway K factor 1. And to extend the modeling swinging states, it requires infractions beyond the band picture. And as you increase electric field, what they observe is that there's a spontaneous RxY, fault resistance appears at the zero electric field at low temperature. Okay, and you see the magnetic hysteresis, and at the low temperature, the value is very well quantized, at least naked eye. Okay, it's not quantized part of part of the thousand, but this is very well quantized to h over e squared. Okay, this is actually transport data. Okay, so this is a plot of the RxY as a function of temperature, or RxY and RxX, and you see that the RxY zero field RxY started to develop around like 4 or 5 Kelvin and become quantized to 2 Kelvin. Right? And, I was told this result has been seen in at least 3 devices from the same Liang Fu. What's interesting is that first, it's an electric field tuned transition from a Mott insulator into a quantum transform. It's already interesting. And even more intriguing is that it does not seem to have any electric field hysteresis. So this makes one wonder if this transition could actually be a continuous transition. Okay. So I put a question mark. Is there some other aspect of the experiment which is difficult to reconcile with this continuous transition? But there's some, for example, the puzzling aspect is that the claim that from the capacitance measurement, the charge gap does not seem to close across this transition. Okay, which I have no idea how it's possible. But anyway, so I'm going to take this as a motivation. The fact that the electric field tuning this transition does not show any hysteresis. I want to explore the possibility of a continuous quantum phase transition. Yeah, between the two. Yes.
The word topological here just means that RxY becomes non-zero.
Become quantized. Yeah. Okay. So now, why this is this kind of quantum phase transition is particularly interesting? Because first it involves the change of topology, topologically trivial into a topologically non-trivial. But also the Mott state and the quantum Mott state are really very different. The Mott insulator, you think it in terms of the particle point of view, particles are localized on two sides, while the topological states, it has, for example, chiral edge states. So this can never be understood in the fully localized picture. But there is a strong difference between the two states. So, is it possible to get a continuous transition? So this is the work with crystal chemical. And what the results is summarized here. So in our picture, it's summarized here. If you take the band structure calculations without interaction, we know at half filling, right? There's two bands. There's a band from the primary majority layer and band from the minority layer. The majority layer is MOT2, the minority layer is WSE2. So, so the Fermi energy is here is half filling, but we are getting factor 1. Half filling of the band majority layer, so the system is actually metal. But then if we increase the Coulomb interaction, right? So we can create a Mott insulating state. But this Mott insulating state is really a charge transfer insulator because we think the copper U is larger compared to the energy difference between the two layers, right? And in particular, the energy difference between two layers, delta is tuned by electric field. As we further increase electric field, we reduce this charge transfer energy. And then above a threshold electric field, this charge transfer energy becomes negative. I mean that the bottom of the charge transfer band, the bottom of the minority layer band, and the top of the lower copper band, they are inverted with each other. So I'm going to show that this scenario of inverting a charge transfer gap in a Mott insulator can lead to a quantum non-small state. Okay, so
Liang,
yes.
Previously, for previous case, you showed nice numerical data that it was dense later.
Yeah.
That the inversion happens.
Yeah.
Here it's suggestion, or you have something behind the suggestion.
So I'm going to show you some theory analysis here, right now. Yeah. So you're asking about the analysis. Yeah. So I'm showing that right now. Yeah. Okay. So this so what is the actual analysis? This here. So so we're going to start with this the Mott insulator state, right? In the Mott insulator, to start with basically electrons on the majority layer, and because of the strong copper U interaction, it becomes a Mott insulator. This is basically a Mott insulator on the Chern lattice, and a common magnetic order state is this 120-degree AFM state where you have the spins pointing along different directions on the 3 sublattices. So this is the state we start with. We assume that the ground state of this Mott insulator is an 120-degree ordered AFM state. And this is also consistent with what's known about the single band Hopper model on the Chern lattice. Okay. Now, and then what we're going to do is we're going to now bring in another the band from another layer. Okay, another layer which is called a B. And what we're going to do is we're going to invoke just the low energy states in this problem. So the low energy states are basically the top of the lower Hopper band, right, on the majority layer, and the bottom of the band on the minority layer. Okay, so that's the approach I'm going to take. I'm going to examine the quasi-particle band structure at low energy. Okay, and we're going to then construct. We're going to try to answer the question. You know, as I reduce the charge transfer energy, how these low energy states change. Okay, that's the approach we're going to take. And this approach is really unlimited control in the following limit. The active energy scale is that the Hopper U is the largest energy scale. It drives the formation of the 120-degree order of AFM state in the first place. But then it's out of the low energy problem. Low energy problem does not involve a big energy scale of U. It only involves the lower Hopper band of the majority layer. And then the next energy scale is the bandwidth. Okay, we are not taking the flat band limit. We are assuming that the lower Hopper band as well as the band dispersive band in the B layer, they're both dispersive with a finite bandwidth W. And then the energy difference between the two bands is controlled by delta. Okay, so finally we consider the hybridization, single particle hybridization between the two layers, which is what creates band inversion at thin factor 2, for example. So this is the ideal energy scale. Yeah. So in this, I want to claim that under this condition, the approach I'm going to describe is really controlled. So we are really only touching upon the low energy states of the quasi-particle bands. Okay, quasi-particle bands. And these bands are the following. There's a lower Hopper band on the majority layer, and these are spin polarized. What I mean is just that there's no spin degenerate. With the magnetic order, 110-degree magnetic order already lifts the spin degeneracy. On the other hand, on the minority layer, before band inversion happens, the minority layer is unoccupied. So then naturally the spin degenerate states on the minority layer. So then I can write down a continuum field theory describing just the low energy quasi-particles. So in the case of 120-degree magnetic order on the Chern lattice, it is known that the lower Hopper band has a maximum at just the gamma point, k equals 0. And for the other layer from the DFT calculation, we know that the band edge is also at the k equals 0 gamma. Right? So this leads to a three-band model of the quasi-particle spin polarized band from the lower Hopper band, and then the spin degenerate states from the other layer. And the hybridization between the two interlayer coupling has a P-wave form factor that really comes from just the band symmetry analysis. I know, again, we also divide explicitly. And then on top of that, we should put all allowed interactions. And one interaction is this, the density interaction between spin up and spin down electrons on the minority layer. And we will see that this interaction is the only one that is that will potentially play a role. So I want to also emphasize that this situation is very different from the band inversion in topological integers. This is in topological integers, we always have a situation that there's equal number of valence in the matching band, right? It's either spin degenerate matching band, spin degenerate valence band, but they can invert each other. That's what happens at second factor 2. But here we have a fundamental asymmetry. The lower Hopper band is spin non-degenerate, while the high Hopper band is spin degenerate. It turns out that this asymmetry is actually crucial. Okay, and also I want to say that the degeneracy at k equals 0 for the minority high transfer band is actually vigorously protected by a symmetry of the column. There's a threefold lattice rotation symmetry. There's also a symmetry which is time also combined with spin S3 rotation, and this guarantees, this allows basically two type of representations at k equals 0, 1D representation and a 2D representation. How much time? 5 minutes? Okay, sounds good. Yeah, almost done. So this is let me first analyze this problem. Let me first just analyze this problem without this interaction term. Okay, and this is how the band evolve. So as you reduce the charge transfer energy, this band goes down, and then it touches the bond. Blue band touches the red band, and after that, the blue bands now become the lower than the red band, right? But interestingly, notice that we always maintain a filling factor 1, right? So the temperature potential has to be such that only one band is occupied. So this is why after band inversion, the temperature potential has to be exactly at the red band touching point. Okay, so this is all coming from analyzing the 3x3 matrix. So what we see is that after band inversion, there's a quadratic band touching that appears right at the Fermi level. And this kind of quadratic band touching is intrinsically unstable to interactions, no matter how weak it is. This is just similar to the DCS instability. You basically have a finite density electron and holes, and they're perfectly nested. Okay, so that's known from other contexts before. This means then that this interacting term, right, G, will become marginally relevant after band inversion happens. Okay, after band inversion. And if you think about this, the interaction tree is between spin up electrons and down electrons on the B layer, and that's exactly the two degenerate states after band inversion at the Fermi level are exactly all from the B layer. Okay, so that's why this interaction can open up a gap. So once this gap opens, it's known as the quadratic band touching with gap opening, it creates a Chern number, and the sign of the Chern number is determined by the direction of the spin splitting. So interaction spontaneously provide the spins on the B layer, and the sign of the number depends on the spin correlations, either up or down. So this leads to a quantum non-small state. But interestingly thing is that in the span inversion, it only involves low energy states, especially in the majority layer. We start with the 120-degree order state in the majority layer, the spins are in the XY plane. So after band inversion, only a small number of low energy states are modified. So in terms of the spins in the majority layer, it's still predominantly AFM, 120-degree order AFM state. Okay, while in the minority layer, the spins become polarized along the direction. Okay, so we have a situation that the magnetism is a non-coplanar. That there's a AFM 120-degree order state in the MOT2 layer, but spin polarized states in the WSC2 layer. Okay, so this is the main result. Basically, by increased electric field, we can reduce the charge transfer energy, and when this charge transfer gap becomes negative, then we call this simultaneous change of topology and a change of the magnetism. The ferromagnetic Z component develops, and the Chern number appears. So basically, what I described is, you can think of it as like a generalization of the sort of band inversion paradigm that's known from before. So in the case of the band structure non-interacting theory, we know that if you invert the spin degenerate matter band with a spin degenerate valence band, this leads to topological band integer, and all this occurs at the unit integer filling. Okay, what I described today is at a half filling of that, like odd integer filling. And in this case, we need interactions to get any insulin states. So it was known before that at odd integer filling, we can get a mod integer and in particular, high transfer insulator, then the insulating gap is between the lower upper band and the high transfer band. But if we can invert, if we can reduce the high transfer energy, we can invert this gap, and this can create a quantum non-small state. Okay. And I think the reason I think this could be interesting even beyond this moire material is that most of the modern insulators are actually antiferromagnetic. Okay, it's very hard to find ferromagnetic models, but antiferromagnetic insulators are common. And if we have a bulk material with 1 electron volt bandwidth, that is still regarded as a narrow gap system, and we can can get antiferromagnetic high temperature. And if we can find some way to tune the high transfer gap bulk material, this may be a way to get actually quantum non-small effect at high temperature. So that's my dream, so to speak. Okay, so basically, the small state and the quantum non-small state actually, not so far apart. So they are actually, connected. And this is picture found online. This is actually the shortest international bridge connecting 2 countries. One is USA, the other is Canada. I don't know which one is topological, which one is not. Okay, so also now the quantum non-small state has been discovered in other contexts before, other systems. The first one is from the Tsinghua University in China in magnetic topological insulator. In recent years, evidence of signatures of the quantum non-small state has also been observed in magic angle graphene. But in both cases, the magnetism is believed to be ferromagnetic, while the case I described is very different. It's relies on this non-coplanar magnetism. I think I can skip the last part, and so let me just summarize. Cover these 2 types of insulating states, both are thin factor 1 in the semiconductor moire heterostructures, the Mott state and the quantum non-small state. They can, at least theoretically, they can be separated by just a continuous phase transition. Thank you.
Let me quickly start with one question.
Yeah.
Since you mentioned cuprates.
Yes.
Charge transfer gap in the cuprate.
Right.
In cuprate, now there is a Jean-Grind singlet, which changes the story completely. So contrast what you are doing with Jean-Grind.
Yeah, no, this is a fantastic question. We're actually exploring, just starting to think about this Jean-Grind singlet. So yeah, I think there's an action question. So if you look at okay, there's an action question. This is fantastic.
Yeah.
So if you look at the Hamiltonian, for example, right? There are 2 sublattices. There's a sort of a hopping between A sublattice between the B sublattice. There's a hopping between A and B sublattice. There's a hover U, and there's a transfer energy. Right. This kind of model, as you said, can also describe the physics Jean-Grind singlet. Right. So while what I'm doing is something that's very different. Right. This is my conjecture. Okay. So by the way, before that, I just want to say, even though what I showed you is a field theory analysis, we also did Hartree Fock calculations and DMRG studies for this model, right? And indeed, we find the quantum non-small state. Okay. Now, how is this? Why don't we define Jean-Grind singlet physics? Right. So first, the Jean-Grind singlet is usually about doping above the thin factor 1. But while here I'm doing everything at thin factor 1. That's the one key difference. Right.
Okay. But I thought the Jean-Grind singlet at the end of the day will give you magnetism with the scale instead of you get theta. So both spins from blue and from red.
That's for sure. That's for sure. So for example, here before band inversion, right? So if I reduce the charge transfer energy, then the energy scale that controls magnetism is no longer be T squared over U. It will be smaller than that. That aspect is the same. But what's the key difference between Jean-Grind? 2 key differences from Jean-Grind. One is that here I'm looking at fitting factor 1. I'm not looking at doping above 1. Second, here the charge transfer gap becomes so small that the charge transfer energy becomes small enough that I can invert the 2 bands.
This is understandable. Yeah. So question in some sense was that if you take this picture.
Yeah.
And apply genre singlet, the effect in genre style is that you have another Hubbard model,
That's right.
which involves blue and red.
Yes, yes.
But you have, of course, already prearranged antiformabilities on the Hubbard band.
Right.
Genre start with different.
That's
You
right.
first get genre
Yeah,
singlet,
so-
and then you do magnitude.
So this will say, I'll say this way that it means that under some circumstances, you cannot reduce the two-band Hubbard model to one band. Yeah. This is an example of that.
Yeah.
Because I don't see any possibility you can capture this topological states within on one band Hubbard model.
More questions? Yeah, please.
Okay, but this may sound a little bit like you have a picture where the two bands touch each other.
Yeah.
That they cross, and like I remember, like you have a change of color because it's just
Change of color?
yeah. I just want to, yeah, exactly. I just want to understand, like,
The color.
how do you determine which band is from which layer after?
Right, the color encodes that. So the red means that it's from the A layer, blue comes from the B layer. So before the band inversion, right, you see the occupied states all come from the one layer, it's all red. But remember that the two, there is actually a hybridization between the two layers. So a generic eigenstates, the color is mixed, it's in between pure red and pure blue, right? But before band inversion, the TAD is small compared with gap. So that's why it doesn't do much. But near band inversion region, you see that generally the color are mixed because there's this hopping TAD.
After that, like
After band inversion, this is purely blue, K equals 0 is purely blue.
but I mean, on the rightmost picture, like,
Right here is all blue. K equals 0.
and so you just tell which layer is from.
Which layers,
by
yeah.
looking at the eigen.
I can say that, okay, exactly, yeah.
And it's crucial for you that it's blue because.
It's
that
blue.
gives-
You can open the gap, yeah, yes, yeah, I should have color bar.
Okay,
Yeah, so I'm just wondering, like, is there clear, like, qualitative transport signature that tells them apart? Like, for example, if I apply external magnetic field,
Right,
would
right.
you have a slightly different dependence?
So, yeah, one way to tell in transport is that it's difficult to probe. So there's some optical studies of the magnetism in this quantum Wigner state as a function of the pi magnetic field. So they do see, I think I have it here, yeah. The backup slide. Yes, here, right. So, this is a recent experiment again from Cornell group. So this is again MCD, which is related to the spontaneous polarization. It's 0 before the band inversion and become non-zero in the quantum Wigner state, right? And this one is interesting. This one is basically it shows both RXY and MCD signal in one figure. The black line is the measured RXY in units of h raised squared, and you see that the RXY is immediately quantized. Okay, immediately quantized. But if you look at the magnetic bipolism of the two layers, it's still keep increasing and then eventually saturates. Right. So I think that is at least consistent with incomplete polarization at the zero field. So, and the polarization keeps increasing as you apply magnetic field. So if it were fully ferromagnetic in the first place, it will immediately saturate. Right, it will immediately saturate. But you can see that's not the case. The MCD signal continues to grow with the magnetic field. Yeah, so that at least I think is consistent with the case of a canted, partially polarized state along the z direction. Yeah.
Okay, I see no more questions. Thanks very much.
Oh, there's one.
Sorry.
Yeah.
Probably the worst possible timing, but so for the mixing between the two layers, was it that you were tuning the displacement field to get the charge transfer insulator to
Charge transfer between the two layers.
Yeah. So it looked like, initially it's spin degenerate, but then you get splitting between them with the displacement field. And I was just curious about what causes that.
It's because of this instability. So, before band inversion, the charge are all in one layer, right? The other layer is unoccupied, so there's no interaction effect on the other layer. But after band inversion, you have finite amount of oxidation on minor layers, and there's induction. So that causes this splitting.
Okay, yeah.
And with this, thanks again.
The adapter, someone's adapter.
We can also.
Yeah, thank you.